Hi, this is I'm Yang Liu at Carnegie Mellon University, and in this talk, I'm going to discuss a recent work with Bhangale, Mark Braverman, Subhash Khot, and Minzer on parallel repetition for three-player XOR games. So first, I'm going to introduce the problem and some background. To start, let me introduce what a K-player game is. I'll start with a one-round game. A K-player game G formally consists of the following objects. Question sets Q1 to QK. Think of these as just finite sets. And also answer sets A1 to AK, also finite sets. Also, a distribution mu over the questions, not necessarily with full support. In fact, most of the interesting examples we consider do not have full support over Q1 cross da 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 cross QK. And finally, we have a predicate V, which takes as inputs an element in the supportive mu, so a tuple of k questions, as well as k answers, and it maps to 0, 1. And when the predicate maps to 0, that means that it's not an accepting assignment. And when it maps to 1, that means that the answers are an accepting set of assignments for the corresponding question tuple. So let me give an example. So here is a two-player game, k equals 2. So the prover basically will first do the following. The prover first samples a pair of questions, because we're in the k equals 2 case, pair of questions q1, q2 from mu, then sends q1 to player 1 and q2 to player 2. Now, both of them, without interacting with each other, will respond with an answer. Player 1 responds with an answer A1 in its answer set. Player 2 responds with A2 in its answer set. And then the game accepts if the predicate evaluated on Q1, Q2, which is the element in the supportive view, and then A1, A2 equals 1. So this is how a one-round game goes. The problem of parallel repetition asks to study the n-fold repetition of such a game, which we denote as g to the n. In the n-fold repetition of the game, the prover samples question tuples q1 to qn. Here, each qj is a k tuple of questions from the supportive mu. And now the ith element of each question tuple q to the j is sent to player I, but all at the same time. So player I receives q1i all the way up to qni all at the same time. And then the player uses these to produce n answers. And then the prover accepts if all n of the games in each coordinate accept all at the same time. To set up some notation, let val g denote the winning probability of a game. And thus val g to the n is the winning probability of this n-fold repetition, which is less. However, it's been known that val of g to the n is not the same as val g to the power n. As what this means is that parallel repetition is not the same as repeating the game n times sequentially, which the value would then just be val of g to the power n. However, in a very fundamental result of ROS, for two-player games, it was proven that if the value of the game is strictly less than 1, then the value of the n-fold repetition does decay exponentially, just not the way you would expect. Here the notation 2 to the omega g of n means it's 2 to the constant times n, where the constant depends on the game g. This is a very fundamental theorem with applications to PCPs, hardness of approximation, communication complexity, quantum information, and more. In this talk, we're going to focus on multiplayer parallel repetition, that is, parallel repetition for more than two players. Despite Roz's theorem, parallel repetition for 3+ players is quite poorly understood. It is known that the value of the game does eventually go to 0. This is a result of Verbitsky. More quantitatively, for games where the support of the question tuples is equal to little q, the proof of Verbitsky invokes the density-Hales-Jewett theorem for length q combinatorial lines. And thus, with our current understanding of the density-Hales-Jewett theorem, the bound you would get for the for the decay of value of g to the n would be something like 1 over log star 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 of n, where the number of stars is about q. Here, log star of n is, recall, the number of times I have to apply log to get from n down to a constant. Log star star would be the number of times I have to apply log star to get from n down to a constant, etc. To make progress on this problem of three-player parallel repetition, recent work of Girish, Holmgren, Mittal, Raz, and Jan studied three-player games where the question set was just over the binary alphabet. So each player gets a single bit. The GHZ game was identified as a particular challenge in understanding three-player parallel repetition with binary alphabets. In this game, the set of questions had size 4. It was all triples XYZ whose sum was 0 mod 2. So it's a subspace of Z mod 2 to the cubed. The answer sets were also just Z mod 2. A1 equals A2 equals A3 is Z mod 2. And here's what the accepting tuples are. If the input was 0, 0, 0, then the answers are accepting if and only if their sum is 0, again, over F2. And if the questions were XYZ for any other XYZ, not 0, 0, 0, then it accepts only if the sum is 1. So the other possible inputs XY0 is 1, 1, 0, 1, 0, 1, and 0, 1, 1, and those accept the answers A1, A2, A3 if A1 plus A2 plus A3 is 1. It's not too difficult to see that the value of this game is 3/4. So it's very natural to ask then, how does the value of the GHZ game decay under parallel repetition in terms of n? Holmgren and Raz used a combination of Fourier analysis and information theoretic techniques together to prove that the value of the game decreases polynomially. The value of g to the n is the most n to the minus omega of 1. This improves significantly over Verbitsky's theorem, which uses the density-Hales-Jewett theorem. Later, Braverman, Minzer, and Khot improved this bound further to exponentially decreasing. We'll explain this short proof of Braverman, Minzer, and Khot later because it's relevant to our results. Now, to get closer to the goal of this talk, notice that the GHZ game is a 3 XOR game. The predicate is of the form A1 plus A2 plus A3 is T of XYZ for some function on the support of the questions to Z mod 2. So in particular, remember that if the tuple was 0, 0, 0, then it accepts only if and only if A1 plus A2 plus A3 is 0, and otherwise it accepts if and only if A1 plus A2 plus A3 is 1. So we call this a 3 XOR game. More generally, in our paper, we consider when Z2 is replaced with any finite abelian group, basically all the same results apply. This is what we call a 3 XOR game. Now we get to stating our results. To state a result, we need an assumption on the distribution mu. We say that the distribution mu over sigma cross gamma cross phi has no z embedding if there are no non-constant embedding functions sigma, gamma, phi, such that the sum of the maps of sigma, gamma, and phi on xyz is 0 for all xyz in the support. So notice that there's constant solutions when they're all 0, but we say that there's no z embedding if there's no non-constant solutions, where these maps are all into the integers. The main result of this work is that if G is a 3 XOR game, such that mu has no z embedding and the value of the game is less than 1, then the value of the game decreases exponentially under parallel repetition. This generalizes the result of the GHZ game. One can check that there's no z embedding and also that the value is less than 1. So this generalizes that result. Now we're going to go over the proof idea briefly. The first step of the proof for any 3 XOR game is to express the winning probability of some set of strategies in an algebraic expression. So remember that a 3 XOR game, the predicate is of the form A1 plus A2 plus A3 equals T of XYZ for some function T on the support to Z mod 2. The capital F, capital G, and capital H denote the strategies. Formally, a strategy is a function from, at least capital F, is a function from sigma to the n to z mod 2 to the n. What this means is that f takes as input an n tuple of symbols in sigma and outputs an n tuple of answers, each in z mod 2. Now for a subset S of n, define the parity function f sub s to be -1 to the power of the sum of f x of I, where the sub I means fx restricted to the coordinate I, and you sum over all I and s. And the ts of xyz be -1 to the predicate t summed over coordinates in s. It is not hard to check that the following relation holds. The probability of the strategy's FGH winning can be given by the expectation over all subsets S, expectation over XYZ and mu to the n, of this following three-wise correlation, FXGYHZ, T of XYZ. Each of them is a F sub S, G S, HS, etc. I'm not going to write a proof in this talk, but it can be seen either through a Fourier analytic lens or as something like the Hadamard code, but it's a simple computation to see that this holds. Okay. Let's try to interpret this expression now and see why it seems like a useful thing to have looked at. Let's consider the n equals 1 case. This is expectation xyz and mu, -1 to the fx plus gy plus hz minus t of xyz. I claim that the value of this is strictly less than 1. Why is this true? Well, the reason that it's strictly less than 1 is because the only way for it to equal 1 is if fx plus gy plus hz equals t of xyz for all xyz in mu. And that's not possible because the value of the game is less than 1. So for the n equals 1 case, the inner expression, when the size of s is 1, the inner expression is just, it's less than 1. Okay? This leads to the following very natural conjecture. For each fixed s, the expectation of x, y, z in mu of fx, gy, hz, ts, xyz is at most 2 to the minus omega size of s for any one-bounded function f, g, h. So why is this a natural conjecture, possibly? It's natural because, well, the way you can think of it is that the n equals 1 case of some like tensor-like expression is strictly less than 1. And thus if I tensor it up to the power s, that the value should decay exponentially. Maybe the one way people can see it is that if you have a matrix and its maximum eigenvalue is less than 1, then if I tensor the matrix, its eigenvalues go down exponentially. And this would be an analog for tensors, basically. Unfortunately, this conjecture is actually false. Let me try to explain intuitively why it's false. Essentially, what can happen is, even though the n equals 1 case has no real valued functions f, g, h satisfying that the expression equals 1, there can be complex valued functions f, g, h where the value is exactly equal to 1. Now, here's how I lift this to a solution for S, but maintain real functions. What I do is I first tensor up f, g, h as complex functions. Then the value still equals 1. And then I take the correct real or complex parts of each of f, g, h, and this will lose a constant factor in the correlation, but that's okay. We have proven that at least the value does not decay exponentially in S. In fact, no matter what you choose S to be, the value will still be lower bounded by some absolute constant. And this motivates the following definition. We call T of xyz non-embeddable if there are no functions f, g, h now mapping to complex numbers where fx, gy, hz is -1 to the T of xyz for all xyz in mu. Now, the previous conjecture can be converted into a theorem. If T is non-embeddable, then for each fixed x, the following correlation is true. It does indeed decay exponentially. While I'm not going to prove this theorem in this talk, the proof sketch is to do induction on the size of S, basically. This is very difficult, and the ideas are based on a paper of Bhangale, Khot, and Minzer and involve several steps. You do induction, you need to ensure that FGH have high degree, etc. There's a lot of steps, but one sentence, you do some kind of induction. Now let's consider the complement, the embeddable predicates. When this T function is not non-embeddable and it's embeddable, there exists FGH where fx, gy, hz is in fact -1 to the T of xyz. What do we do in this case? Well, we use ideas based on the GHZ proof. Let's consider the GHZ equations and see why the GHZ game is embeddable. This requires solutions to the following equations. F0, G0, H0 is 1. F0, G1, H1 is -1, etc. And this does have a solution over complex numbers. Fx equals Gx equals Hx equals I to the x. Using this, you can actually rewrite the GHZ winning condition as fx plus gy plus hz is 1/2 of x plus y plus z. Because, well, basically think of I as being -1 to the 1/2 x. So then T of xyz is -1 to the, well, T of xyz is -1 to the exactly 1/2 x plus y plus z. This is what the GHZ winning condition is. Okay. Now remember, the GHZ winning condition was fx is u hg is 1/2 x plus y plus z, where these are functions from z mod 2 to the n to z mod 2 to the n. Now, multiply the previous equation by a factor of 2 and subtract the x over. This defines functions ax, by, and cz, but now from z mod 2 to the n to z mod 4 to the n, because I've multiplied the whole equation by 2. So the GHZ equation becomes ax plus by plus cz is 0 mod 4. In other words, you have three functions which behave like homomorphisms, kind of, on z mod 4. So using additive combinatorics, what you can prove is that if this equation holds with some non-trivial probability, then A looks very much like a homomorphism from z mod 2 to the n to z mod 4 to the n. And in particular, A of x is basically just an even, like its image is always an even number all the time. This contradicts that ax is 2fx minus x. And this proof can be converted into an argument that the GHZ game, the winning probability is exponential decay. Can we carry out the same argument as the GHZ case in our setting? The big issue is that the distribution mu over Q1 cross Q2 cross Q3 does not have group structure, while the GHZ game has significant group structure. The fix is to use ideas of another work of Bhangale, Khot, and Minzer to enlarge the question alphabets Q1, Q2, Q3 until they capture all the group structure of the underlying distribution mu. Formally, what you say is consider all possible embeddings of mu into finite abelian groups, and then you keep enlarging Q1, Q2, Q3 until they capture all the structure of these underlying abelian groups. This is the part of the argument where we critically use that mu has no z embeddings. If mu did have a z embedding, then there's no finite group that would capture all the embedding structure because you can kind of capture arbitrarily large groups inside a z embedding. So yeah, this is the critical place in the argument where we use that mu has no z embedding. And to carry this out formally, you again have to do several inductions, very similar to the case of non-embeddable predicates, and again are based on previous works. To conclude, we looked at 3 XOR games whose distributions have no z embeddings, and we proved that they admit parallel repetition with exponential decay. At a high level, the proof has the following steps. You algebraize the expression to become a statement about 3 tensors, fx, gy, hz correlation. You handle the non-embeddable case by doing induction. In the embeddable case, you increase the alphabet size so that you capture the case, so you kind of lift to the case where the input distribution has group structure, and then you apply additive combinatorics akin to this GHZ proof to conclude. Since this work was released, more work of Bhangale, Khot, Liu, and Minzer proved new inverse and structure theorem for distributions, this time with z embeddings. And it would be interesting to see if those theorems can be used to extend the results in this paper, and can any of these new inverse theorems in fact prove things beyond 3 XOR games? Okay, so that's all I had. Thanks.